So in our last video we have studied how to design a symmetric inverter. Like we have studied some basics of symmetric inverter design. Now we will see how can we design a symmetric inverter and how can we set the ratios of width and length of our MOSFETs. So in our last lecture we have studied this beta n and beta p ratio, which basically defines how our width and length are related to each other. And we have also seen that these kn and kp are set during processing, such that these are these two values are set something so that this ratio comes out to be 2 and 3. Obviously 2 to 3 range, not 2 or 3. And we also define the mobility, this mobility ratio. This ratio is basically mu n by mu p, and mu n basically is the mobility of electrons and this mu p is mobility of holes. So in our designs, this mobility of electrons is much higher than mobility of holes, around 2 to 3 times. So this ratio comes out to be 2 or 3, it varies from 2 to 3. And a symmetric inverter must have equal input logic low and equal logic high voltage ranges. It means के अगर हमने एक इन्वर्टर डिज़ाइन करना है जो कि एक सिमेट्रिक इन्वर्टर हो, तो उसकी जो मिड पॉइंट होना चाहिए वो हाफ VDD पे होना चाहिए, so that we have input logic low and output input logic high, and equal input logic low and equal input logic high ranges. So in an example we will see how can we design a symmetric inverter and what factors we need to calculate before designing in our tools which are microwind or cadence or Mentor graphics. So to design a symmetric inverter, we have to design a symmetric inverter, we have to satisfy this condition, that is Vm is equal to 1 by 2 VDD. So earlier we have this expression that we solved in our previous video, where we have seen that Vm minus Vtn whole square is equal to, this is equal to beta p by 2 into VDD minus Vm minus VTP whole square. So we say that we have to satisfy this condition. So if we have to satisfy this condition, I can replace these values here, this Vm and this Vm here, with 1 by 2 VDD, obviously VDD by 2. So our updated expression says that this is our VDD by 2. So if I solve this expression for beta n and beta p ratios, that are beta n by beta p, which is equal to, this 2 cancels out here and obviously here. So this beta n and beta p will be equal to VDD by 2 minus VTP divided by VDD by 2 minus VTN. So this is whole square as well. So we can say that if this expression VTP is equal to VTN, then we can say we can design a symmetric inverter if we choose beta n is equal to beta p. To understand this equal beta and beta p phenomena, we can calculate, we can solve an example. To solve this example, we have to consider a case, may I write it in different form, consider a case like where we have PMOS, like, and it has with following parameters. So we have process which has these different parameters. The parameters are Kn bar is equal to 140 microampere per volt square, K bar P is equal to 60 microampere per volt square, and then we have VDN, which is equal to plus 0.7 volts. We have VDP, which is equal to minus 0.7 volts, and the VDD is given by 3 volts. So if we consider beta n and beta p values are equal, what would happen then? Like, for example, we consider beta n is equal to beta p. So what happens is, like, we can say that this will be a symmetric inverter. This will be symmetric inverter. So how can we verify this, using our formulas which we derived earlier? We can verify this using this VM expression. This VM expression was VDD minus VDP plus this beta n and beta p ratio, and then we have VDN as well. This was divided by 1 plus square root of beta n by beta p. Here in this expression, or in this example, these ratios are equal to 1. So we can say that, and this VDD was equal to 3 minus obviously 0.7 plus 1 into 0.7. This is divided by 1 plus 1. If we solve this expression, like this 0.7, like this 0.7 here and this 0.7 here cancels out each other, and we are left with 3 by 2, or we can say that, we can say that this is equal to Vm and this is equal to VDD by 2, which is equal to 1.5. Like this is equal to 1.5 here, 1.5 volts. So we can say that this will be a symmetric inverter. So to design this inverter, we have to know that what will be the aspect ratios of our design. For that, we have to to know the design aspect ratios. What we have to do is we have to solve this expression which we have seen earlier in this session, which is equal to Kn bar divided by Kp bar. This is equal to W by L of N divided by W by L of P. And we have seen here in this previous expression, this is equal to 1. If this is equal to 1 and we solve our this part of our equation for ratios, this will be equal to W by L of P should be equal to K bar of N divided by K bar of P, and this will be equal to W by L of N. So this K bar of N, W by L of N. If we put the values of Kn and Kp, we have 140 by 60 and W by L of N. If we solve this expression, this turns out to be around 2.33. Like this expression, this ratio here is 2.33. So what does this mean, this ratio? This means that if we have a ratio of 2.33, it means W by L of P is equal to 2.33 times W by L of N. Means कि हमारा जो P FET है that should be 2.33 times larger than N mos. So our P mos should be larger than our N mos. Just to check what would happen if we use same aspect ratios. Like if we use same aspect ratios, what would happen? Like if we have W by L is equal of W by L of NMOS and W by L of PMOS, both are equal, then what would happen? Like for that we have to solve this same expression here. Like we have to look at this expression. We have like this K bar P, and then we have these ratios W by L of N and W by L of P. So in this expression these two are equal to 1, and we can say that if we have solved this these two terms earlier, this was 2.33, so we can say that beta N by beta P is equal to 2.33. And obviously if we solve for our midpoint voltage using this beta N ratios, that would be equal to Vm is equal to like 3 minus 0.7, and our beta ratios are 2.33, that is multiplied by 0.7. This is divided by 1 plus root of 2.3 and 3. So this results to be 1.33 volts. So we can say that this will not be a symmetric inverter. अब ये इन्वर्टर क्यों नहीं होगा? Because like our Vm is less than VDD by 2. Like our Vm was 1.33, that is less than obviously 1.5. So this condition is not satisfied, and we can say that our inverter is not a this is not a symmetric inverter. One other thing that we have to observe is like our Vm in earlier case was 1.5, and now we have Vm is equal to 1.33. At this point our beta N ratio was like beta N and beta P was equal to 1, but now we have beta N and beta P which is equal to like this was equal to 2.33. So we can say that if we increase beta N and beta P ratio, then Vm like shifts to the left.
or we can say that the curve for this was the curve for we can say that this was for beta n by beta p is equal to 1, and then now this curve will shift something like this when we have beta n and beta p is equal to 2.33.
So we have seen that हम एक इन्वर्टर कैसे डिज़ाइन कर सकते हैं, एक सिमेट्रिक इन्वर्टर कैसे डिज़ाइन कर सकते हैं. In our symmetric inverter we have seen like the size of PMOS is higher, like around 2.3 times higher than this NMOS. This shows a different inverter. Like this has equal size inverter, like equal width inverter. So this is not a symmetric inverter. It will not give you an output which is equal in equal with equal delay. So this inverter which has higher PMOS, like higher PMOS area than our NMOS, it will give us like a equal inverter. So we can say that larger PMOS for symmetrical inverter like this one, and so that we can achieve VDD like Vm is equal to VDD by 2, and then we have equal size PMOS and NMOS which are like shown here. But in this design, the midpoint voltage is less than VDD by 2, so this is not a good choice for our symmetric inverter. And like if we have this ratio like beta n by beta p, अगर इसको हम like increase करेंगे इस ratio को, तो हमारी जो VM है basically वो reduce होती जाएगी. Like for example, if we have beta n by beta p is equal to 1, then we have this curve for this design. If we have beta and beta p by beta p is equal to 0.5, then this curve shifts to the left, and then we have a similar like settings for like 2.5 as well. So if we have to shift our VM, this midpoint voltage to our left or to our right, we have to change this ratio for our beta and beta p. So this is it for our symmetric inverter designs. In our next video session, we will study we will design an inverter, how obviously following all these rules, कि उसको हम किस तरह से डिज़ाइन करेंगे. That will be a practical session as well. So this is it for today. I will see you next video session inshallah.